Hello everyone from Math 2200, Discrete Mathematics. It's Professor Wenson here again with a video on your ZyBooks Section 6.7 titled Equivalence Relations. Alright, so in this section we're going to see an example of a type of special relation called an equivalence relation. So you've seen relations, and you've also seen properties of relations, like, is the relation reflexive, anti-reflexive, or neither, symmetric, anti-symmetric, or neither, and is it transitive or not? So you've seen all those in a previous section. So we're kind of putting all this stuff together here, and we'll see what an equivalence relation is in a second. All right, it's a relation with the reflexive property holding, the symmetric property holding, and the transitive property holding. Right, we'll see all that. Okay, so, like I said, a relation R is an equivalence relation if R is reflexive, symmetric, and transitive. Okay, all three. If a relation R is an equivalence relation, then the notation A tilde B, like A with a little squiggly line between B, A and B here, is used to express A is related to B. So this is what we've been used to seeing in previous sections, right? A R B or A S B or whatever the name of the relation was between the two elements. Well, now instead of saying A is related to B, I mean, you could still say that A is related to B, but in these equivalence relations, right, relations with these three properties, you see this notation. You can also now kind of say that A is equivalent to B. Now, that doesn't mean that they're necessarily equal values. Like if we're talking numbers, they may not be equal numbers, but they're equivalent in the sense that, A is related to B and B is related to A, right, because of the symmetry. Right, if it's a symmetric relation as well, Okay, so I'll probably still just say related. A is related to B, but if you see the special tilde symbol between the elements, it means we're in an equivalence relation. All right, so they say here, consider an example where the domain is a set of all people. Define relation B such that X is related to Y, X, B, Y, if person X and person Y have the same birthday. The relation B is reflexive, right, since every person has the same birthday as him or herself. Right, there'd be if you were making a graph, right, there'd be a self loop on every single person. The relation is symmetric, right, because if X has the same birthday as Y, then Y has the same birthday as X, right? So again, if you were looking at a graph, that means, if X has an arrow going to Y, then you're going to see an arrow going right back to X, from Y to X, and that's always happening for every pair of values, X and Y, for every pair of people, X and Y, with the same birthday. And the relation is also transitive, right? Because if X and Y share a birthday, and person Y and person Z share a birthday, well then X and Z must also have that same birthday. Right? So if there's an arrow from X to Y and an arrow from Y to Z, then there's also an arrow from X to Z, right? For any pair, any values for any people X, Y, and Z. If you're seeing the first two arrows, you're seeing that third one. Right? So the birthday relation would be an example of an equivalence relation. Okay, so So here's one where they would say, you know, if two, they'd say that person X, and then they'd have that little tilde symbol here. Person X tilde Y is really, now you see there, they, you know, if you say X, person X is equivalent to person Y, all that would mean is that they have the same birthday, right? They're not the same person, right? They're not actually equivalent in all aspects, just in this aspect of having the same birthday. All right, so they give an example here, and I'll play this animation. So we have a set A with elements, you know, A, B, C, D, E, and F, and an equivalence called R on set A, right? And they drew up all the arrows, right? All the relationships. So it's reflexive, because remember, to see reflexive means every single element is related to itself. So you see the self loop on every single element. It is, you know, symmetric, because every time you see an arrow going in one direction between two elements, you see the arrow going in the opposite direction as well. So A to B, B to A, you know, A to E, E to A, B to E, E to B, you know, F to D, D to F. Every time you see an arrow going between two different elements, you're seeing the arrow going in the opposite direction, for every pair of elements. So it's symmetric and transitive, right? When you see an arrow, you know, between X, you know, A, see, I'm seeing there's A to B, B to E, so there should be A to E. I'm seeing that, you know, E to A to B, so there should be E to B. You know, and this is always happening, always happening. You know, D to F, I'm sorry, D to F, F to D, so there should be D to D, right? And the self loops are there. But yeah, that's always happening. When you see the, you know, two connections, there's that third connection. So yeah, and then they say blah blah blah. Okay, no. All right. So they said if they added for some reason, right? If they added the edge from E to D and that was it, then it would no longer be transitive, and therefore not an equivalence relation anymore. All right. But the original picture without this dotted edge, the original picture was representative of an equivalence relation. Reflexive, symmetric, and transitive all at the same time. And another thing about this picture, right? Another thing about this picture, forget this, forget that I already showed you this, but do you see how when you have, this is gonna happen too, and this is brought up later in the section. When you have an equivalence relation on a set, like this is here on the set A, do you see how this equivalence relation naturally kind of breaks set A up into separate pieces? See how they're not, you know, there's this piece over here of the graph with elements A, B, and E that's separate from this piece here with elements D and F, and that's separate from this piece here with just element C. So what we're going to see in a minute is that an equivalence relation determines a partition of the set that you have the relation on. Remember, a partition is, you know, you're breaking a set up into non-overlapping pieces. So I have a partition of set A here with, you know, A, B, and E being one part of the partition, then D and F being another part, and C being the third part. But we'll see that in a second. All right. So here, again, you just got to run through the three properties. Is the relation they're describing reflexive, symmetric, and transitive? It's got to be all three to be an equivalence relation. If any one of those fails, then it's not an equivalence relation. Okay, so here we're asked to select the choice that applies. Here, the domain of R, relation R, is a group of employees at a company. And they're saying that X is related to Y employee X is related to employee Y if employee X earns at least as much money as employee Y. So that means, the amount of money made by person X is greater than or equal to at least the amount of money made by person Y. And it says also there are at least 2 employees at the company who do not earn the same amount of money. Right? So they're telling us there that not everyone makes the same amount. Okay. All right. So first off, is it reflexive? Does every employee make at least as much money as themselves? Yeah. It's equal. You make the same amount of money as yourself, so you're definitely making at least as much money as yourself. So it's reflexive. Is it symmetric? Is it symmetric? No, no, it's not. Because again, they said there are 2 employees that don't earn the same amount of money. There are at least 2. So take the 2 of those people that don't earn the same amount of money. Now the person who makes more money, that person is related to the other person. So say person X makes more than person Y. So X would be related to Y, but not the other way around, right? Because person Y doesn't make at least as much as person X. So the relation described here on this set of employees is not an equivalence relation because it's not symmetric. Okay, so you just gotta do a little thinking. All right. How about the domain of relation R is the set of integers. All right. So integer X is related to integer Y if X squared equals Y squared. All right, so is it symmetric? If I take an integer X, is X related to X? Is X related to itself? Yeah, X squared would be equal to X squared. Any integer squared would be equal to that same integer squared. So it is reflexive. Is it symmetric? Well, let's see. If X is related to Y, that means X squared is equal to Y squared. Would Y be related to X? Well, yeah, if X squared is equal to Y squared, then Y squared would be equal to X squared. So it is symmetric. And finally, is it transitive? All right, so if X is related to Y, meaning X squared equals Y squared, and Y is related to, say, Z, then Y squared would be equal to Z squared. Would X be related to Z? Well, yeah, if X squared equals Y squared and Y squared equals Z squared, then through that chain of equality, you would see that X squared would be equal to Z squared. So then, yes, X would have to be related to Z. So the way this relation is described on the set of integers has all 3 properties. It's reflexive, symmetric, and transitive. So this particular relation would be an equivalence relation. All right, and I will leave this last one for you to think about. Okay, so now another definition. Right. So if A, set A, is the domain of an equivalence relation, and an element, little a, belongs to set A, then this notation here with the brackets around A, this bracket around A thing is defined to be the set of all the elements in A that are equivalent to A, or related to A. Remember that little tilde symbol meant equivalent, when we're talking about equivalence relations, right? They mentioned there was an equivalence relation here. So this is called this little bracket around A set. this is called an equivalence class, or the equivalence class of element A. And again, it contains all the elements in the set A, capital A, that are related to element little a, or equivalent to little a in the equivalence relation. So let's consider an example in which the domain is a set of natural numbers, right? Natural numbers. So 0, 1, 2, 3, 4, 5, etc. And x is related to y, or equivalent to y, if x and y have the same remainder when divided by 3. Now, when you divide by 3, you can get remainders of 0, 1, or 2. And that's it. Right? Whenever you divide by n, right, if you divide by an integer n, your possible remainders are 0, 1, 2, all the way up to n minus 1. Right. So then, so again, x is related to y, or equivalent to y, if x and y have the same remainder when divided by 3. So they give us some examples here of what are called, again, equivalence classes. So the equivalence class for 0 is the set of all natural numbers whose remainder is 0 when divided by 3. Alright, so let me go to a piece of paper. I'll pull up a piece of paper on the same page here. Okay. Hopefully I'm writing this big enough. So for this relation, right, the equivalence class of 0, this brackets around 0, is a set. And again, it's a set of all the elements that would be related to 0 in this relation. Remember, two natural numbers are related here if they have the same remainder when you divide them by 3. So this is all the elements that have a remainder of 0 when you divide them by 3. So that would just be the multiples of 3. So in this equivalence class of 0, you'd have 0, you'd have 3, you'd have 6, 9, and so on. Right, you'd have all the multiples of 3 in this set. Now you could also call this, this could also be called the equivalence class of the number 3. Right, because this also contains all the elements related to 3, right? 3's in here. You could also call this the equivalence class of the element 6, because this contains all the elements related to 6. Right? All the elements that are equivalent to 6, and so on. Right? So, but usually we'll use like the smallest element that represents the set. So yeah, all these are the same though. Right? So if you're like, hey, the equivalence class for 0, and I got the equivalence class for 3, these are the same set. So there's no need to copy it twice. There's no need to write them both. Right. All right, then the equivalence class for 1, because again, notice 1 is not in here. This is going to contain all the elements that are related to 1. Well, if you're related to 1, that means you have the same remainder when you're dividing by 3, and when you divide 1 by 3, the remainder is 1. So this set is all the elements that have a remainder of 1 when you divide by 3. All the natural numbers with that property. So 1's in there, of course. And then really I just can keep adding 3. 4 has a remainder of 1 when you divide by 3. 7, 10, 13, and so on. And like I said, with the first one, with the equivalence class of 0, you could say it was equivalent, was the same as the equivalence class for 3 or 6 or 9 or 12. This equivalence class for the number 1, you could also say was the equivalence class of 4, or the equivalence class of 7 or 10 or 13 or 16. Because again, they have the same elements. They are the same set. but we're usually going to, we're usually going to use the element, the smallest representative of that set in the equivalence class notation. Alright, and then finally here, right, the only other remainder you can get when you divide by 3 is 2. You can get remainders of 0, 1, or 2. Right, so then the equivalence class for 2 is, the set of all the elements that are equivalent to 2 or related to 2 in this relation. So the elements that have a remainder of 2 when you divide by 3. So 2 is in there. And then I just keep adding 3, really. 5 would have a remainder of 2 when you divide by 3. 8, 11, 14, 17, etc. And again, like I was saying up top, this equivalence class for 2, you could also say was the equivalence class for the number 5, or the number 8, or the number 11, or whatever. They're all the same set. Now, something I'm noticing. The equivalence class for 0, the equivalence class for 1, and the equivalence class for 2 form a partition of the natural numbers, right? This was an equivalence relation on the natural numbers. So this equivalence class for 0 set the equivalence class for 1 and the equivalence class for 2 form a partition. And you've seen the word partition before, back in the chapter 3 on sets. Form a partition of the natural numbers. Remember, this capital N looking thing was the natural numbers. Now remember what a partition is, and we'll get to it again in a second, but none of these overlap. They're all what they call pairwise disjoint. And again, you saw that definition back in chapter 3. That means none of these have any overlap, right? None of these sets, none of these 3 sets share any elements. So they're pairwise disjoint, and if you were to take the union of all 3 of them, you'd form, the entire set of the natural numbers, right? Because you got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right? You got all the natural numbers represented by each of these sets, and there's no overlap. All right, so these 3 sets break the natural numbers up into non-overlapping pieces. That is a partition, and every single equivalence relation on a set will help you determine a partition of that set. And vice versa. If you know a partition of a set, that will help you define an equivalence relation on that set. And we're going to get into all that stuff right now. So you see, equivalence relations have a special mathematical structure described in the following theorem. Right? So they say, consider an equivalence relation on a set A, and suppose we have 2 elements that belong to A. Right? So if X is related to Y or equivalent to Y, then as I was saying with the page I was wrote up earlier, then the equivalence class for X will be the same set as the equivalence class for Y, because they're related. Right? If it is not the case that X is related to Y, so if X is not related to Y in the equivalence relation, then the equivalence class for X and the equivalence class for Y will be disjoint, or mutually exclusive. They won't share any elements. All right, and I'll let you read the proof for that here. And now here comes to what I was saying. This theorem can be used to show that an equivalence relation defines a partition of the domain, a partition of the set that the relation is on. And I've already mentioned this. A partition of a set A is a set of non-empty subsets of A that are pairwise disjoint and whose union is A, right? So they're non-overlapping sets that form A when you take their union. Right. Let's do an example here. Well, this is just the same picture from earlier. Right, this picture here. And they're showing you how it's a partition of set A. You got A, B, and E, D and F, and then C. So you have three equivalence classes, three different equivalence classes, three different parts that this set is broken up into. So that's all they're showing you down here in this, and I'll play the animation. Alright, so again, R, this is the same equivalence relation earlier. And you see it defines a partition on A right there. They put a circle around the whole thing because all the elements A, B, C, D, E, and F are in set A. And they put these little non-overlapping, non-empty circles that form the partition. See the set with A, B, and E, the set with D and F, and the set with C, right? Form a partition of set A. They don't overlap, they're pairwise disjoint, and if you were to take the union of all three, you'd get set A. Right. You can read all that. Alright, so here's an example, and I'll actually draw this one up on a piece of paper. So here, they gave us this set A with elements A, B, C, D, and E. And they gave us R, this relation on set A, so a bunch of set of ordered pairs where every component of the ordered pairs is coming from set A. Now they told us, right, they said R is an equivalence relation. Now you can go through and verify that, is it reflexive? Is it symmetric? Is it transitive? Right. So what I'm going to do is draw a picture. Right. There's only 5 elements here, right? So I'm going to draw a picture, and we're going to see how this equivalence relation R will help us define a partition of set A. Right? We're going to break set A up into non-overlapping pieces. All right, so remember those. Now, what I'm going to do first, before I draw the picture, actually, yeah, I'm going to make these equivalence classes. So what's the equivalence class for element A? Right, so remember, the equivalence class of an element is the set with all the elements that are related to that element, right? So, A, you see A is related to, A is related to A here. So A is obviously in the equivalence class for element A. A is related to E, so E is in here. And that's it, and E is related to A. And again, the equivalence class for set A, for element A, would be the exact same thing as the equivalence class for the element E. Alright, but I'm only going to use one of them, right? There's no need to use both of them. So I'm going to use this one. I'm going to use the equivalence class of element A. Alright, so that takes care of these ordered pairs. Right? Also E to E. Right? E to E, because we're talking about all the elements that are related to A and E. Alright, so that takes care of A and E. So how about B? Right, what's the equivalence class of element B? So again, the equivalence class of an element in an equivalence relation is just the set of all the elements of the set that are related to it. Right? So what elements are B related to? Well, B is related to B. Right? B is related to B. It has to be that way because an equivalence relation is reflexive. And that's it. That's the only B. Those are the only B's I'm seeing in any of these ordered pairs. So that's the whole set. So the equivalence relation, the equivalence class of element B is just the set with B in it. So that takes care of A, B, and E. Again, I'll use this set as part of my partition of set A. Let's do C. Now the equivalence class of element C, again, it's just the set of all the elements related to C, or equivalent to C. Well, C is related to D, and of course itself, right? So C and D, and then you got D is related to C, and D is related to D, but D is already in there. And again, you could call this also the equivalence class of element D, because they're all the elements that are related to D. But no need to use both of them though, right? They're the same set, so I'm just going to use this equivalence class of element C. And if I want to make a graph, I'm going to make the graph so you can very clearly see the partition. You can see the breaking up of set A into separate non-overlapping pieces. So say here's element A, and element E. And then here's element B, and then elements C and D. I'll start drawing these relationships. So we had, C was related to D, and it's got to be symmetric. So D's got to be related to C, but we'll get to that, right? A is related to E. A is related to A. B is related to itself. D is related to C. C is related to itself. E to A. D to D. And finally E to E. So there's a directed graph of this relation. And then to make it pretty similar to what they had in the last animation, I'll make kind of a Venn diagram here. And if I put a box around all these elements, this is set A, right? It's got all A, B, C, D, and E in it. And then do you see how we can partition A to the set with A and E? I'm going to just break, there's set A and E. And then, just with set B. And then the rest of it is, I break it up into pieces. I break it up into non-overlapping pieces, partition it. Right? So there's that set with A and E, then in this circle here, this part here, there's this set with element B, and then in the rest of it is with C and D. So I've broken up set A into non-overlapping pieces. Right? And then again, another way we could say this is that the set with A and E, comma, the set with just B in it, and the set with C and D in it. Right, these three sets form a partition of set A. Right. Yeah, but every equivalence relation on a set does this. Right. So there may be some other equivalence relation on this set, that would break it up into different kinds of pieces. But every single equivalence relation does this to its domain. Breaks it up into these equivalence classes that partition the domain. Okay. All right, and that's it. And then this one here, right? It was A and E. It was this one, partition 2. Right? And then you have your additional exercises. Right, so like, first, I think the first one here is just, is the relation that's being described an equivalence relation? And then, if the relation is an equivalence relation, then describe the partition defined by the equivalence classes. Right. So how would it break up the domain into those non-overlapping, those non-overlapping groups, those non-overlapping pieces? And again, some of these are assigned, some are not. I would still recommend, though, doing all of them, because you can check your solutions here, see how you're doing, just to get more practice and more exposure to the material, get better at it. And as I've said every video almost, please don't just look at the solutions and copy them. Try to work out the problems, try to figure things out before you resort to looking at the solutions. Because if you're just copying solutions and not actually practicing, you're not going to learn anything. Alright, hopefully this video is a reasonable guide. Just got you a little introduction to equivalence relations, and brought partitions back and talked about those again. Hopefully it's a nice guide for you when you work on the 6.7 stuff on your own. And of course, if you have any questions, let me know. And thank you very much for watching.